Now we shall discuss about biasing of transistors. As I explained earlier in one or two of my classes, for a transistor to work as an amplifier, it is necessary that I mentioned that it is necessary that the base emitter junction is to be forward biased and the base collector junction to be reverse biased. Only in that situation the transistor works in the active region and it acts like an amplifier. Now the question is, how do you provide this biasing? By using, naturally it is by means of external voltage sources. Now how do you, with using what kind of circuit and using how many voltage sources really you can provide the biasing is important. And before that, selecting a biasing point known as the operating point in the volt ampere domain is another important thing to be carried out before designing an amplifier. So let us now discuss about the transistor biasing. Please look at this diagram. Please recapitulate that a transistor, either NPN or PNP, with this kind of notation, that is the base current as the current going inside and the collector current as the current coming inside into the transistor, and the emitter current as the current going out of the transistor. So the current relationships are like this. The collector current is approximately beta times IB. So this has been already discussed in the earlier chapters. And the emitter current is IC plus IB. It's approximately equal to 1, therefore IB plus beta IB, which is equal to 1 plus beta IB. And for normal operation, at typical voltage and current operations, like a base current of the order of 100 microamperes and the collector current of the order of 5 to 10 milliamperes, the base to emitter potential is approximately 0.7 volts. It may be between 0.6 to 0.7 volts depending on the current. For low values of base current, it may be about 0.6 or 0.65, and for high values of base current, it may be 0.7 volts. So irrespective of the current value, it is approximately equal to around 0.7 volts, the base to emitter potential is. So this is what is what a transistor has when it is biased in the active region. In this saturation, for instance, before that let me mention this. This is the characteristics of a typical NPN transistor of this type. The beta for this transistor is about 100. So that's why when the base current is 50 microamperes, the collector current is about 5 milliamperes. Similarly, when this is 100 microamperes, collector current is 10 milliamperes approximately. Hence beta is 100 in this particular example. Now this is the collector to emitter voltage and collector current characteristics, or the output characteristics. Now the question is, at what point do you operate a particular transistor? Do you operate the transistor at Vc is equal to 6 volts and Vc is equal to 6 volts and IC is equal to 10 milliamperes, or do you operate it at 4 volts and 15 milliamperes? So this is the question in biasing. So first we select the biasing point. That means the biasing voltage VCE and the biasing current IC. This is known as the Q point or quiescent point, because when no alternating signal is given as input, the transistor works in the works with the DC conditions. It is quiescent. It works with the quiescent conditions. Well, it produces, say, a base current of 100 microamperes, and it produces a collector current of 10 milliamperes, and collector to emitter voltage is 6 volts. So this is how it is specified. Hence it is known as a quiescent point, because under quiescent conditions the voltage across the collector to emitter, between the collector and emitter and the collector current, indicate the quiescent point. And specifying VCE and IC is good enough, because given beta and given IC, you know how much is IB. IB is IC by beta. And given VC as about 6 volts and IC as something like, say, 10 milliamperes, we know that this transistor is in the active region. That means the base to emitter junction is forward biased, and obviously the voltage difference is of the order of 0.7 volts. Since this is obvious, it is not necessary that this be specified. Once it is in the active region, and which is indicated by VCE and IC itself, that is good enough to state that the transistor is in the active region, and this is the voltage and this is the current. And other information like VBE and IB are derivatives of this. So the point where you are operating the transistor under quiescent conditions is known as the quiescent point, and this is the biasing. This indicates the biasing voltage and biasing current. Okay, first you have to select the point and then make a circuit and see that this transistor operates at that point. Then the transistor would be ready for working as an amplifier. Then you feed a signal and you will get an amplified signal at the output. So I explained about what is biasing and the importance of selecting the biasing point, and what is the sequence in which you should go about. Now let me explain something biasing point. There are a few considerations in selecting the biasing point. The considerations are as follows. Selection of Q point, let me write it, selection. You see that the transistor operates in the linear region, in spite of the signal swing and the characteristics are linear around the quiescent point. You should see that the characteristics are linear around the quiescent point. If you apply a sine wave, it should remain as a sine wave at the output. It should not have some distortion as far as possible. So we select an operating point in the linear region as far as possible. These are the two important considerations in selecting the Q point. So let me explain each one briefly. Please look at these characteristics. Now here base current is 100 microamperes. Quiescent base current is 100 microamperes. Now if you incorporate a signal in the base to emitter junction, and then as a result of that, if the base current has an AC swing which is more than, whose peak value is more than 100 microamperes, then what happens? When the added signal over here to the between the base and emitter, because of the added AC voltage, if the AC current tries to be more than 100 microamperes, for the negative swing, the quiescent current plus the alternating component tries to go down to 0, go below 0. And when it goes below 0, the transistor is, when the base current becomes 0, the transistor is cut off, collector current is 0, and you will not have, when the collector current is 0, you will have distortion in the output. Hence the transistor goes out of the linear region, or the active region. Similarly, the transistor should not saturate. If the collector current increases, the transistor may go into the saturation, the instantaneous operation may be somewhere in the saturation region. So that one also gives rise to distortion, which you will learn about it later, So to see that the transistor operates in the active region, it's not, I won't call it as a linear region, active region in spite of the signal swing, that is an important criterion. Next, the characteristics are to be linear. That means for a sinusoidal input, it should give you a sinusoidal input. For a particular music signal, it will give you the same music signal. The distortion should be as low as possible. If you look at the input characteristics over here, for a transistor, so please note that in this region here, the transistor has a nonlinear relationship, voltage has nonlinear relationship with the base current, whereas in this region it has a good linear relationship. It is approximately linear, and it is predominantly linear in this region. Therefore, we should try to operate the transistor at this particular VB and at this particular IB. Then if you apply a sinusoidal change in the base to emitter potential, you will get a sinusoidal change in the base current, and that sinusoidal change will give rise to sinusoidal change in the collector current, and that will give rise to an amplified sinusoidal voltage change across the collector resistance, and that gives you the same signal and a replica of the input signal, amplified replica of the input signal. So that's what is desirable. On the other hand, if you try to operate this transistor around this point of VBE and IB with this kind of base to emitter potential variation, so what do you expect? The base current to change from this value to, so this value centered around S. So you will find that the resulting base current is not sinusoidal. For a sinusoidal base to emitter potential, the resulting base current is not sinusoidal. There is some distortion already. The negative swing in the base current would be smaller than the positive swing. Only when it is equal and it is sinusoidal, you say that it is distortion free. So if you operate the transistor in this region, and then when you impinge the alternating signal over it, you will have distorted variation in the base current if you operate it in the nonlinear region. On the other hand, if you operate in the linear region, you will get linear output. Hence, it is important that the Q point is selected for in the linear region for amplification applications. There are certain applications like some nonlinear applications where purposefully we operate the transistor in the nonlinear region. Okay, so these are the important criteria. Now, how do you, once the Q point is selected, how do you operate it? How do you make the circuit give rise to this kind of Q point? We have seen that with one source for the base to emitter junction and with another source for the collector to between the collector and emitter, we can provide biasing. We can provide biasing with this kind of arrangement. What are the requirements? I repeat, the requirement is that it should be about 0.7 volts. The base current should be the required collector current, quiescent collector current, let us call it as VCQ, Q indicates the quiescent current, ICQ divided by beta is the IBQ, and this should be 0.7 and IBQ should be this much. Then, so given that ICQ, so this voltage VCE should be equal to VCEQ. So that is the requirement. I repeat, given VCEQ and ICQ as the requirement, quiescent requirement, now with a circuit, through a circuit arrangement, you see that you get the corresponding VBE of 0.7 volts, VCEQ, VCE equal to that particular VCEQ maybe 6 volts, and the collector current to be equal to ICQ, and naturally the base current to be equal to ICQ by beta. Of course, beta is also specified already once the transistor is selected. Now, what kind of arrangement? Is it that you go for 2 voltage sources and 2 resistances and provide this quiescent point, or can it be done with 1 voltage source, in which case what is the circuit is the question. See, naturally it is better if we can do the biasing for this junction as well as this junction, for both the junctions. If both the junctions can be biased through a single source, then it is advantageous and it is economical. Okay. Hence, it is desirable to go for a single source circuit. We have different circuits available for biasing the transistors. We have fixed biasing circuit, where we use a single voltage source VCC is used to bias both the junctions. Now, the base current and the required VBE are provided through this resistance RB, and the required VCQ is provided through the collector resistance RC, and the current ICQ are provided by RC. So, the same supply can be used for both. Now, the question is how to select this RB and RC to provide a particular VCQ and VBQ. If you analyze this circuit, it will be clear to you. Now let us analyze a given VCC and given RB and RC. Let us analyze and see what kind of quiescent point does it give, how much of ICQ does it give, and how much of VCQ does it give. So that's the question. Let us analyze it and see. Now this is a positive supply applied through a resistance to the base emitter junction. Okay. So what does it mean? So naturally, so you are applying a positive potential to the base emitter junction through this resistance. Now if VCC is greater than 0.7 volts, certainly it is going to drive some current into the base emitter junction. And irrespective of the current, so the voltage drop is about 0.7 volts. If the current is low, the voltage drop may be 0.65 volts, VBE may be 0.6 volts. If the current is very high, it may be 0.72 volts. So in any case, irrespective of whatever is the value of IB, VBE is going to be of the order of 0.7 volts with a close approximation. With a close approximation, VBE is 0.7 volts. So with this as VBE, how much of current flows here? How much of IB flows here? Now if you apply Kirchhoff's voltage law to this side, how much current flows through RB? Apply Kirchhoff's voltage law on this side. VCC is equal to IB into RB plus VBE. So IB into RB plus VBE is equal to VCC. From this naturally IB is equal to VCC minus VBE by RB. So this RB, because only IB flows through this RB, and this is of the order of 0.7 volts. So if this is 12 volts as an example, if this is 12 volts and this is a silicon transistor means the base to emitter potential is 0.7 volts, and RB is say 240 kilo ohms. In this example, how much of IB do you expect? IB is equal to 12 minus 0.7 by 240K, and that is equal to about 47 microamperes. IB is equal to 47 microamperes. It is very simple. If you want to provide an IB of 20 microamperes, so RB would be VCC minus VBE by IB, the 20 microamperes. So 12 minus 0.7 by 20 microamperes, that much of RB is required. So this is as far as IB is concerned. Now if beta is given as 50 for this particular transistor, that is known and it is specified by the manufacturer, and when beta is equal to 50 for the transistor and with IB equal to 47 microamperes, collector current is known to be beta IB. Okay, this is our equation 1, this is equation 2. So with this relationship, 50 into 47 microamperes is equal to 2.35 milliamperes is the collector current. 2.35 milliamperes is the collector current. Now let us look at the output side. At the output side, if you apply Kirchhoff's voltage law to this mesh, so you will find that VCC is equal to RC IC plus VCE. So this is the equation which governs the output side mesh. Now IC is known, beta IB is IC, and if you substitute that here and given RC, VCE can be obtained. This is the third equation. Therefore VCE is VCC minus RC IC, or IC is beta IB, so RC beta IB is equal to VCE. So now this equation tells you how much is the VCE. This is how we can analyze the circuit and get the quiescent point. Given the circuit values, you can get the quiescent point. As a design, this is the analysis here. As a design, when you are required to design the circuit, the Q point is given to you and you have to find the circuit parameters. You have to find what circuit to use and what are the values of the resistances, etc., to be used. So this design procedure, the design procedure is a reverse operation. So you know that this equation, so this equation and this equation governs the circuit. Relates the quiescent values with the circuit parameters like RB and RC. Now with given VC, VCE and IC, and naturally given beta once the transistor is selected, you have to find out RB and RC in the design problem. So there also you use the same equations to get the design. Okay, so you should practice designing the circuits, biasing circuits given quiescent points. Any questions on fixed biasing? Yeah, there are no questions. Let me proceed with the biasing, other biasing circuits. And before going to the other biasing circuits, please note that the fixed biasing circuit is a very simple circuit. Analysis is simple and design is also simple. It is governed by simple equations. That is the advantage. But it is associated with some disadvantages too. So what are the disadvantages? Now in this circuit, if I replace, just 1 second before going through that, for this particular value of 2.35 milliamperes and given RC is equal to 2.2 kilo ohms, we will find VCE as 6.83 volts. This is VCE. Now if this transistor with beta equal to 50 is replaced by another transistor with beta equal to 100, so let us see what happens. If you have another transistor with beta equal to 100, why am I saying like this? The manufacturer, when he says that this is a transistor, the transistor has a beta between 50 to 150. That's how a manufacturer specifies. That is because of the inaccuracies in the manufacturing process. He specifies that beta for the transistor is between 50 to 100 or between 50 to 150. If you pick up one transistor, it may exhibit a beta of 50. If you pick up another transistor, it may exhibit a beta of 75. Another one may give you 100. So this kind of uncertainty would be there because of the errors in the manufacturing process. it is possible to reduce the errors in the manufacturing process at the cost of money. But if you want a cheap transistor, so one has to go for a simpler manufacturing process than accurate processes, and in which case you will have this kind of inaccuracies. Now, if beta is equal to 100 in this particular case, let us redo the analysis. Do you expect any change in IB? Because the IB is VCC minus VB by RB alone. It is not connected with beta. Therefore, IB is going to be 47 microamperes. Then what about IC now? IC is 100 times IB, 4.7 milliamperes. With IC equal to 4.7 milliamperes, how much would be VCE? VCE is 12 minus IC into RB, that means 4.7 into 2.2. How much is that? It is 1.9 volts. Say 2.6 volts. So now earlier the Q point was 6.83 volts and 2.35 milliamperes. Now the Q point is 2.6 volt and 4.7 milliamperes. Where is it located in the characteristics? So earlier Q point is 6.8 volts, let me 6.83 volts somewhere here, and IC is 2 volts. So this is the Q point. Now the Q point is, it's about 2.6 volts and 4 milliamps. The Q point is this. The Q point has shifted from here to here with the same circuit, but with a replacement of the transistor by another transistor of the same type. The Q point is shifted by so much. So the Q point may shift from a linear region to a nonlinear region. A Q point may shift from a deep active region to an edge of the active region, which is undesirable. So with the fixed biasing circuit, so the disadvantage is that with changing transistors, the Q point will get shifted, the Q point gets shifted. That is one disadvantage. There is another disadvantage. The other disadvantage is that when temperature rises, the Q point shifts, the quiescent point shifts. What happens is, when temperature rises, we know that IC naught rises. IC naught gets doubled for every 10 degrees rise in temperature. And when temperature rises, if IC naught rises, and increased IC naught makes IC to increase, because IC is beta IB plus 1 plus beta into IC naught. That term is also there. So because of that term, IC increases with increased temperature. And when IC increases with increased temperature, the power dissipation in the transistor, that is VCE into IC, the power dissipation in the transistor increases. And that will further give rise to rising temperature in the transistor. And with rising temperature in the transistor, IC further increases. And increased IC further increases the temperature. And ultimately you will find that the transistor goes into, the transistor gets burnt. First of all, the Q point gets shifted. This is known as thermal runaway. Due to a temperature rise, the transistor Q point shifts and ultimately it may get burnt. So this kind of a thing happens, may happen with fixed biasing circuit. In other words, the fixed biasing circuit is unstable for temperature variation or with temperature variations. Unstable with temperature variations. This is one drawback, and the other drawback is sensitive to device variations. If you change the device, that means if you change the transistor, the Q point shifts. So that is the other drawback. So because of these two reasons, a fixed biasing circuit is not a good circuit. Then what are the other circuits that are available? You have the self-biasing circuit, so that is available and it gives you a good stability. So let us look at the self-biased circuit. In the self-biased circuit, it is similar to the fixed bias circuit, but it uses another resistance in the emitter. So it can be driven by a single resistance supplying the base current, like in the fixed bias circuit, but it uses an emitter resistance. Alternatively, the base side, base emitter junction side or input side biasing is provided with two resistances instead of one resistance. So this kind of circuit is also used. So this circuit is known as a self-bias circuit or emitter to base biasing circuit. Now, how does this circuit improve the stability? That's the question. Let us consider the case of temperature variations. When collector current increases, what happens? What happens to the drop across the emitter resistance? When collector current increases, even for constant base current, emitter current also increases. And as a result, the voltage drop across the emitter resistance increases. When the voltage drop across the emitter resistance increases, what happens to the voltage drop across the base to emitter junction? So this side is supplying a potential here, and the output, the potential, and that potential is being shared between base to emitter junction and the emitter resistance. Now, a tendency to increase the collector current increases the emitter voltage drop across the emitter resistance, and this voltage drop tries to reduce the base to emitter potential. And when it tries to reduce the base to emitter potential, why? Because so this voltage is equal to this plus this, and when one of these two tries to rise, the other one has to decrease because the input side is constant. So when you do that, it tries to reduce the base to emitter potential. When base to emitter potential decreases, naturally IB decreases, and when IB decreases, collector current decreases. So a tendency to increase the collector current reflects as a reduction in the collector current. So because of this kind of feedback effect, it gives you bias stability against temperature variations. And The same thing happens, a similar thing happens due to device variations also. When the beta is increased, for instance, to 100 from 50, when beta is increased, what happens to the collector current? Collector current increases. And when collector current increases, what happens to the voltage drop across the emitter resistance? So this one increases. And when this increases, the VBE decreases by a huge amount. And when VBE decreases, IB naturally decreases. And the decreasing IB decreases the collector current. This is how, to device variations also, it is very sensitive. I mean, it is insensitive to device variations, and it is stable against device variations, and it is stable against temperature variations. Now let us analyze this circuit. On the input side here, if I treat this as being supplied like this, so there is a supply here, VCC, this is R1, this is R2, and this is going into the base. So this circuit, input side circuit, is being redrawn in this fashion. This is going to the base point of the transistor, this point, base point. Now, if this base current is negligible compared to the current flowing through R1 and R2, how much would be the voltage here? The voltage here would be VCC into R2 by R1 plus R2. If this is negligible, please note that this VCC gets divided between R1 and R2. Therefore, this voltage is going to be VCC into R2 by R1 plus R2. That is the voltage between the base point and the ground point when this is negligible. When this is not negligible, how do you simplify the circuit? We can simplify the circuit by considering its Thevenin's equivalent between these two terminals. Thevenin's equivalent between these two terminals. And according to Thevenin's theorem, this circuit can be replaced by a Thevenin's voltage source in series with a Thevenin's resistance. This circuit can be replaced by that. So if you do so, the circuit, input side circuit gets simplified, and the number of equations to analyze the circuit decreases to 2 from 3 equations. As such, this can be analyzed with one mesh equation here, and one mesh equation here, and one mesh equation here. You have to solve 3 equations. Now, by using Thevenin's equivalent, I will reduce it to 2 equations. Now, you know that V Thevenin is equal to equivalent to VCC into R2 by R1 plus R2. That means when this is open circuited, what is the voltage which appears across this terminal? That is V Thevenin. That is equal to VCC into R2 by R1 plus R2. This is V Thevenin. And R Thevenin is equal to, when the resistance looking into the terminals, when the voltage source is replaced by a short circuit. So please note that then the resistance is a parallel combination of R1 and R2. Therefore, R Thevenin is equal to R1 R2 by R1 plus R2. Now, with the input side circuit replaced by its Thevenin's equivalent, we can see that the circuit gets simplified to this form. So this is the circuit. This is V Thevenin, R Thevenin, and this is the circuit. And we know that this is VBE. Therefore, the Kirchhoff's voltage law in this mesh gives us V Thevenin equal to R Thevenin into IB plus VBE plus the voltage drop across RE, and the voltage drop across RE is equal to IE into RE, and IE in terms of IB 1 plus beta into IB into RE. This is one equation. Here I have substituted this equation. IE is 1 plus beta into IB. And the output, at the output side, VCC is equal to the drop across RC, that is RC into IC, and IC is beta IB. I am trying to reduce the number of variables, plus VCE plus the drop across RE, that is 1 plus beta into IB into RE. Now what are the unknowns here? The Q point is the unknown, that means VCE is not known and IC is not known, RIB is not known. We know that VB is of the order of 0.7 volts, and we know beta, and RE, R Thevenin, V Thevenin, and VCC and RE are known. So now by solving these two equations, we can find out VCE and IB, thereby IC can be determined, and that gives the Q point. So this is Q point analysis. And in the design problem, given VCE and IC and beta, thereby IB, you have to determine RC, RE, R Thevenin. You have more number of unknowns here. By choosing one, we can find the values of the others. Properly choosing one, we can find the values of the others. And we shall continue this lecture in the next class.